Hello, I'm Charlie Thompson, and this is the Too Long I Didn't Read the Chapter on Climate Change lecture slides video. I thought I would quickly go through what the high points are, try to tie everything together so that when you dive into the actual chapter, everything is more connected and less, what the hell's going on here? So this is an animation by NASA, by their Scientific Visualization Studio, showing global temperature anomalies from 1880, which is the first year that we had reliable temperature from thermometers, up to 2019. The bluer it is, the cooler it is relative to normal, relative to an average. So it's not showing actual temperatures. Up here in the upper left-hand corner, there's a little scale showing this like orange color is 1 Celsius degree warmer than average, and this darker red is 2 degrees warmer. This light blue is 1 degree cooler than average, and this is 2 degrees cooler than average. So I thought that, yeah, picture's worth 1,000 words. So you can see much of the world. There's pockets where the temperature is higher, but it looks like most of the land is pretty blue. So I'm going to hit play, and we're going to see changes. This would be weather. The changes that we're seeing are weather. Those are short-term changes, but the overall long-term trend then would be climate. So now we're up into the 70s, we're up into the 80s, 90s, 2000s, and here we are at the end. So it looks now like just about everything except for the tip of Antarctica and this blob, the blob in the North Atlantic. The blob in the North Atlantic is one of the standout areas where the temperature is cooler, where there's a negative anomaly. And that is because of the melting ice water, because Greenland is melting. As Greenland is melting, the water runs into the ocean and cools it. So there's this big pool of cool water caused by melting glaciers, caused by climate change. But you can see most of the world's pretty red. It looks like the higher latitudes in the northern hemisphere are redder than the mid-latitudes, at least for the United States. Going north from Mexico to the US to Canada, looks like Canada has a much higher temperature anomaly. Same thing going from Africa up into Eurasia. And then if we bring it back to the beginning, because one of the things that happens is people get used to the way things are. So taking it back to the beginning, you can see there's been a dramatic shift. A dramatic shift in the overall temperatures on Earth. Cool. So let's take a look at something else then. So this is a cartoon from a website called XKCD, a webcomic of romance, sarcasm, math, and language. And it's a timeline of Earth's temperature. It's a cartoon starting 20,000 years ago, with the temperatures on Earth roughly 4 Celsius colder than they are today, about 4.3 degrees cooler than present temperatures. At that time, Boston was buried under a mile of ice, and glaciers reached as far south as New York City. So Boston under a mile of ice. So when we talk later in this chapter about 4 degrees of warming, 4 degrees of warming melted a mile of ice. There were ice sheets to New York City. Boston was under a mile of ice when conditions were 4 degrees colder. Now they're 4 degrees warmer, and they're about to get another 4 to 8 Celsius degrees warmer. But people say things like climate's changed in the past. Well, that's true. So this is what we're going to look at, is how much climate and temperature has changed over the last 20,000 years. So 20,000 years ago, I'll just keep saying it, a mile of ice over Boston. The world is starting to warm. 20,000 years ago, we were coming out of the last glacial maximum, the coldest period with the largest extent of ice recently in Earth's history, 20,000 years ago, and then everything starts melting back. The ice sheets are retreating. They're getting smaller. So here's the temperature. Each of these boxes is 1 degree. So that's 1, 2, 3, 4 degrees cooler, 4.3. So we're still about 4 degrees cooler. And now things are beginning to warm up and warm and warm. Massive glacial outburst floods across the Pacific Northwest, creating the channeled scablands. There's some videos that I've posted about that. Amazing stuff. Ice sheets. Chicago, ice-free and proud 12,000 years ago. Temperatures start to decline a little bit in the northern hemisphere, and then warming continues. So now we've got 10,000 years ago, we have human cities. We have large-scale farming. Saber-toothed cats go extinct. Now we've reached modern temperatures. Rising seas cut off the Bering Land Bridge between North America and Asia. Cattle domesticated. So about a half degree warmer, a little cooling. People figure out 5,000 years ago how to work with gold. Proto-Indo-European language develops. Permanent settlements in the Fertile Crescent. 3,000 years ago, Stonehenge. Last mammoths on a tiny Siberian island go extinct. Now we've got coming up on 0. There you go. Paper. And slight cooling. This led to frozen canals in the Netherlands, that half degree. Now we are here and we're zipping off towards someplace between 4 and 8 Celsius degrees of warming. But if I start at the very beginning, you can see not a whole lot of change, not a whole lot of change. Gradual warming over 20,000 years. Gradual, not a lot of change. Still cooling, and then wham! Everything starts to go up. So this is an unusual portrayal of this data set. Let's take a look at another way of showing it. All right, and now the lecture slides with, as promised, another way of looking at that. So this is, I think, the most important data set that we have. This is comparing temperatures in Antarctica with carbon dioxide levels for the last 800,000 years. This is the Epica Dome Sea Ice Core. We've drilled down and recovered ice that's about 1 million years old. We've analyzed 800,000 years worth of ancient ice that tells us the carbon dioxide level in the atmosphere and also the temperature at the surface. So you can see over the last 800,000 years, carbon dioxide levels have gone from about 180 parts per million, 180 parts per million, to about 280. 280 conditions are similar to the present. 180, there's a mile of ice over Chicago. 280, it's like the present. 180, 180 parts per million carbon dioxide, it's a mile of ice over Chicago. 280, like now. 180, mile of ice over Chicago. At 280, we were beginning to go back into a glacial colder period, except humans figured out how to burn fossil fuels on a gargantuan scale. So now carbon dioxide, this is old. This is from, I think, 2007, 2008 sometime. Carbon dioxide is now over 400 parts per million. So we've gone from a high of 280 to 300 parts per million. CO2 is now over 400 parts per million, and it's not going to come down in our lifetime. So this is the most important. This is it right here. Carbon dioxide goes up and down and up and down and up and down in this more or less regular clockwork 100,000 year cycle of 10,000 years of warm and 90,000 years of cold caused by changes in Earth's orbit around the sun. Now the temperature is changing dramatically. Carbon dioxide is changing dramatically, and that's because of humans. That's the big difference. Climate has changed in the past. Climate has changed dramatically in the past. As climate changed in the past, it was because of natural forces. The difference is it's now all 99.9% driven by humans. So this is a graph of temperature. This is the last 1,000 years of temperatures on Earth. This is a condensed version of what we were just looking at, the 20,000 year record. This is also sometimes called the hockey stick. This was developed by a man named Michael Mann, Dr. Michael Mann. He won a Nobel Prize for his contributions to science for assembling this data set. It's been widely attacked by conservatives because they didn't like that it showed that it's warm now. In fact, he was sued by the Attorney General of Virginia, who demanded all of his research because they accused him of faking it. A climate change denier group reanalyzed all the data and issued a press release and said, "Oh, I'm sorry, I guess he got it right." So that was a big, the Berkeley Earth reanalysis project was a really big deal because it was funded by conservative dollars. And when they looked at the data, they said, oh yeah, I guess he's right. It's warmer now. So climate change, what are we going to talk about? How do we know about past climates? The answer is it's called proxy data, but it's really tubes of stuff, and I'll explain that. How do we know about past climates? Not thermometers. We didn't have them. They didn't exist. Tubes of stuff. Why is climate change in the past? Earth's orbit. Boom. Done. Most of it. How do we know climate's changing now? Because we can pay attention. We have thermometers. We have satellites. How do scientists model climate change? With big computers. And how are governments and people responding to climate change? Well, the governments are responding by not doing anything, and the people with money that work for the fossil fuel companies are responding by peddling lies and disinformation to pump up their profits. So let's go through this. Proxy, there's that word, proxy, P-R-O-X-Y, you ain't got no alibi, it's proxy. Proxy records are a record of something that tells us about something else. So with a thermometer, it gives us a direct reading of temperature. A proxy record, the best example I can give you is the movie The Hangover. So in the movie The Hangover, they were trying to figure out what the hell happened, and they didn't have direct records. They had proxy records. So they had a receipt that told them that somebody might have been someplace. That's a proxy record. Real proxy records are things like plankton, fossil plankton, gas bubbles in ice, ocean sediments, fossil pollen, very important source of data, fossil pollen, growth rings on trees, mineral formations in caves, coral reefs, all of those are sources of data about past climates. Here is a lady researcher holding a tube of dirt that has been cut in half so that they can look at the layers of dirt. This was drilled out of the ocean floor. Here you can see other ocean sediment cores. Here is project leader Dorte Dahl Jensen of the University of Copenhagen. I believe this was the Epica A project, and this is showing the last tube of ice from the very bottom, showing bands with dust and debris in them. Here's fossil pollen. You can see that they are different shapes, and each species of plant has pollen that is distinctive. So this light green one is a different species than the orange, is different than the pink, is different than the blue spiky, is different than that yellow thing, is different by these squishy blood cell looking things, is different from that COVID looking thing. So by looking at fossil pollen, we know what plants lived there. If you know what plants lived there, you know what the climate was like. So you can use plants to backwards engineer. That's the way proxy data works. You have to backwards figure out what was going on. If you know what the plants are, you know what the climate was like. For example, if you're looking at oak trees now and grass pollen, but in the sediment cores, you're finding lots of pine trees, that tells you the climate used to be cooler and wetter. And now because you have oak trees rather than pine trees, the climate is cooler and drier. So that's one way you can use fossil pollen. There's a ship with a drilling rig that they use to take these sediment cores from the bottom of the ocean. Here's a snow pit showing the layers of snow in Greenland. Over time, more snow falls and it compresses the snow on the bottom, squeezes out most of the air bubbles. But here is a cross section of a tube of ice. So they took a saw and took a cross section, and you can actually see the bubbles. So this, they wouldn't be able to use for scientific analysis because it's been exposed to the ambient air in the atmosphere, so it's contaminated. But they have ways that they can cut the ice and keep it fresh and uncontaminated and actually analyze the gases in the ice to see what the CO2 content was back in the day. There's a great video about Willy Dansgaard and isotope analysis. Isotopes are different forms of a same molecule, and they can tell us about, for example, temperature. The video on Willy Dansgaard does a great job. I'm not even going to bother to try to explain it. O16, O18, looking at the ratio of O16 to O18 tells us if conditions were colder or warmer. So looking at oxygen isotopes, the O is for oxygen. Looking at oxygen isotopes in ice, it'll tell us what the temperature was when that ice was deposited. And the Willy Dansgaard video does a great job of explaining it. Looking at trees, we know narrower rings like right there and like right there. Narrower rings mean that it was probably a drier year, wider rings, a wetter year. So we have a climate record in the American West going back 20,000 years or so, looking at tree ring data. And by taking samples from different trees, we can piece together a continuous record. Like no one tree is living for 20,000 years. I think the bristlecones may be up 5 or 10,000 years old for bristlecones. I make that closer to 4. Yeah, but if it was 4, that'd be like a redwood. Anyway, so trees, you're looking at like 4,000 years maybe. But by piecing together, because the patterns are dictated by the climate. So if you can find overlapping sections, you can piece together a continuous record, and that's what scientists have done in the American Southwest, is put together a 20,000 year record of climate from tree rings, which also then allows them to date structures. Like this house, if they find wood, the wood has tree rings, they can date the tree rings. I mean, they could do radiocarbon dating as well, but they can also do tree ring dating and say, oh, for example, this Pueblo structure built by the Anasazi was built during this time period because that's what the tree rings tell us. So lots of cool stuff you can do with tree ring data. This is the last 500 million years of Earth's climate. And really the important part we're going to talk about is the last million years and then the last 20,000 years. And I'm briefly going to mention that Earth's temperature has gone like way up, way down. There's been a couple times of Snowball Earth, and I'll talk about that in a second. But for the last 50 million years, Earth's climate had been generally cooling. Over the last 10,000 years, there was a slight cooling trend until we started burning fossil fuels, and then the temperature is going to shoot up. So Snowball Earth, back in the day, the PETM, the Paleogene Eocene thermal maximum was this spike in temperature we think caused by methane, which is a greenhouse gas. Methane exists as ice in the ocean, and if it thaws out, it's a very potent greenhouse gas and would result in rapid warming of the planet. We think that's what happened roughly 54 million years ago. And it's kind of alarming because it gives us a preview of what could happen on Earth today as it warms at an equally rapid rate. Too long, didn't read. Mass extinctions, really bad, really, really bad. Snowball Earth, as Earth gets colder, you get more snow, which reflects light, so it gets colder, so you get more snow. So there's a couple feedback loops and tipping points. Once it gets cold enough, you just get a runaway covering up of Earth of snow and ice, which then makes it colder. And eventually they think most of Earth was covered with ice and snow, except maybe some open water close to the equator, but they're not even really sure about that. They think over time, volcanic activity led to an increase in carbon dioxide in the atmosphere because there was no plants, right? Everything was covered with ice, so nothing is absorbing carbon dioxide. If volcanoes emit carbon dioxide, it accumulates in the atmosphere, which warms the atmosphere, which breaks it up. So it's just a good thing that as Snowball Earth progressed, it allowed carbon dioxide to build up, which then triggered the melting of everything. But it's interesting. Totally fascinating. So here we've got the last 50 million years. There's been this cooling trend. Over the last million years, Earth has been in this cycle of roughly 100,000 years, 100,000 year glacial, interglacial. The warm parts are interglacial. The cold parts are glacial periods. About 90,000 years of cold, 10,000 years of warm, 90,000 years of cold. We were heading into another glacial period, but then we started burning fossil fuels, and now we're bouncing back up. Again, there's that map showing temperatures, bing, or rather carbon dioxide and temperatures over the last 800,000 years, the last 1,000 years. You can see a gradual cooling trend over the last 1,000 years, right up to the mid-1800s when we started burning fossil fuels. Boing, and then temperatures go up and up and up. Yeah, this is temperature, not carbon dioxide. So yeah, the red are direct measurements and the blue is proxy data. There you go, proxy data. Corals, tree ring, ice core. So the reason that we go back and forth between these glacial and interglacial periods is Milankovitch cycles. Earth's orbit changes shape bunch of different ways. The shape, the direction Earth's axis is pointing at, and the amount of axial tilt, all those change on a cycle of 100,000, 26,000, and 41,000 years. I'll post some videos on it because, again, videos worth a million words. So the orbit changes shape from being more circular to being more oval. The tilt gets more and less, and Earth's axis wobbles on a 26,000 year cycle, going from pointing at Polaris right now. In 13,000 years, it's going to point at a star called Vega. And then you can see the effect of glaciation, the effect of wobble, of axial tilt, and the ellipticality of orbit. All three of those things on totally different 100,000, 26,000, 41,000. They come together to make this cycle of approximately 96,000 years. From interglacial to interglacial, approximately 96,000 years as the result of these three combinations, which have driven climate in the past. Except now climate is changing very rapidly at a time when you can see we should be heading back into another interglacial period, but we're not because of carbon dioxide. So some people say, is it sunspots? No, you can see insolation increases and decreases by less than 1 watt on a 22-year cycle. Here's temperatures over the same time. Here is numbers of sunspots. No, it ain't sunspots. This is just fun. About 20,000 years ago, last glacial maximum. I keep saying there was a mile of ice over Boston. I've included a couple pictures to show the extent of glaciation. And all the brown was land. So you could actually have walked from Malaysia to Indonesia to Papua New Guinea to Australia. All of that was entirely walkable as dry land. There was no, 20,000 years ago, was no English Channel. The coast was about 60 miles offshore in New York. And in California, you could have walked all the way from Marin out to the Farallon Islands. All of that would have been a broad coastal plain with grasslands and herds of bison and mammoths and antelopes and lions and tigers, at least saber-toothed tigers. This is Doggerland. This is another one of those crazy, crazy things. This is the way Earth looked 20,000 years ago. Or 16,000 years ago. Ice sheet over Scotland, ice sheet over parts of Ireland, but all of the green was dry land. So you could have walked from Belgium or France to London and never gotten your feet wet. Over the last 16,000 years, as the ice sheets melted, sea level has come up, drowning all of this light green by 7,000 years ago. And let's see, by 16,000 years ago, that was dry. 8,000, that was dry. 7,000, that was dry. And now all of the green is underwater. And Dogger Bank is an area where fishermen started bringing up things like antlers with their nets and wondered, how the hell do you get antlers way out here in the middle of the North Sea? And the answer is, well, people lived there. 16,000 years ago, anyway. So Milankovitch cycles are the dominant driver for Earth's climate. That's what creates this cycle of glacial and interglacial. Other factors play a role in changing climate. For example, plate tectonics. So 220 million years ago, all the continents were together, blobbed up like that. So there was just one big ocean. So as the water goes along the equator, it gets warmer and warmer and warmer, and then it goes up towards the poles. But all one ocean, incredible continentality. And then as the continents broke up, of course, all of that changed. So one of the things you probably never thought about, two things I'm going to tell you. One is that the Panama Land Bridge is relatively recent. So 20 million years ago or so, when that closed up, it created the Gulf Stream. The Gulf Stream as a current didn't exist before 20 million years ago because that water was passing through. So water from the Atlantic was then warm water from the Atlantic was passing through into the Pacific. So the Western Pacific would have been warmer. The Western Atlantic would have been cooler because that warm water would have been squeaking by into the other ocean. And the other thing I wanted to say is 40 million years ago, when India rammed into Asia, causing the uplift of the Himalayas, it exposed massive amounts of limestone rock to rainfall. As rain fell on the limestone, the carbon dioxide in the rainwater dissolved the limestone, taking carbon dioxide out of the atmosphere, cooling the planet. So the uplift of the Himalayas cooled Earth. because it absorbed carbon dioxide from the atmosphere, which I find totally rad. In this case, chemical weathering causing a change in temperature is the result of absorption of atmospheric carbon dioxide. That's fascinating. So we've got tectonics playing a small role. I think I've mentioned before, the uplift of the Sierras would have made Nevada into a rain shadow, into a desert. Same thing would have happened with the uplift of the Andes as a result of plate tectonics. Atmospheric gases. So volcanic eruptions create lots of ash. Albedo blocks the sun. Temperatures drop for a couple of years. Temperatures drop for a couple of years. Temperatures drop for a couple of years post-volcanic eruption. We've had some biggies. The Long Valley eruption covered much of the United States in ash. 600 feet of glowing ash in parts of California. That volcanic ash is volcanic glass. It's very sharp. It can cause enormous lung damage. Climate feedbacks. Let's talk about feedback loops. So we're looking at something happening that then causes something else to happen more, positive feedback, or happens less, negative feedback loops. So all the positive feedback loops I know of are positive. All the feedback loops for climate are positive. They're all bad. So we've got ice albedo. It's a positive feedback loop. Ice melts, becomes dark ocean, absorbs heat, makes it warmer, melts the ice. It's pretty much it. Ice reflects a lot of light. When it melts, you get water, which absorbs heat, which makes it warmer, which melts the ice. So that's a positive feedback loop. This is the ice sheet. This is Greenland. In lecture every semester, when this slide pops up, I usually haven't looked through my slides since last semester, so I always forget that it's thrown in here. And I always wonder, why do I have a shot of Hawaii, of the basaltic oh shit, no, that's not lava. That's not a parking lot. That's the ice sheet in Greenland. You're supposed to be all like white, but no. Black carbon from ships, ash from forest fires. So there's two positive feedback loops right there involving ice and albedo. As the ice in the ocean melts, there's more ships, so there's more exhaust, so it melts more ice, so there's more water, so there's more ships. That's a pretty big one. As it gets warmer, there's more forest fires. The forest fires create ash. The ash melts the ice, which warms the planet, which causes more forest fires. So we've got the ice albedo loop, and then little subloops for Arctic shipping and Northern Hemisphere wildfires. Another close-up of the ice sheet. Water vapor. As the atmosphere warms, you can have more water vapor. Water vapor is a greenhouse gas. The more water vapor you have, the warmer the atmosphere is. The warmer the atmosphere is, the more energy there is to evaporate water. So you get more water vapor because there's more water vapor. It's a greenhouse gas. So we get bigger storms, and we can measure the amount of water vapor in the atmosphere. It's increasing. We can measure the energy released by storms. That's increasing because of the water vapor feedback loop. Carbon. Let's talk about carbon. I made those words big because they're important. You got sources. Sources are places that emit carbon, cars. Sinks are places that store carbon, like plants absorb carbon dioxide, so plants are a sink. Soil absorbs carbon dioxide, that's a sink. And then flux. Flux is the carbon that goes back and forth between sinks, or from sources to sinks. Carbon sinks are places where carbon is stored. Flux is carbon moving back and forth between sinks. And the amount in flux is 1/10 to 100th of the carbon in sinks. So most of the carbon is just sitting there. Little tiny bit is going back and forth between sinks. Yeah, it should be balanced, but it's not. Humans are making more, right? So on this, let's see, yellow is sources. Yellow is taken up in sources. White is stored in sinks, and red is emitted by humans. So every year, plants take up 120 gigatons of carbon. And then when they break down after they're dead, they release 120 gigatons. Plants globally are picking up another 3 gigatons of plant because of increased carbon dioxide in the atmosphere. If you pump more carbon dioxide into a grow room, you get more plant growth, which works great until as the temperature rises, plants use less carbon dioxide. So right now, we're seeing increased plant growth because there's more carbon dioxide. But as the temperature continues to increase, the rate of photosynthesis will decrease and plants will actually take up less carbon dioxide, even though there's more of it, just because it's too warm. They're tired. They need cool temperatures to rest, and that's not going to happen. So 10,000 gigatons stored in carbon, 6,000 gigatons stored in sediments in the ocean, 40,000 stored in the ocean, 8,000 gigatons of carbon in the atmosphere, 2,300 gigatons in carbon. Some of this is in permafrost. And so when the permafrost thaws and microorganisms break down this carbon, it gets released to the atmosphere. So this 60 gigatons could potentially increase dramatically. I think there's this would be 3 times as much carbon stored in the soil as there is in the atmosphere. The Keeling Curve, CO2 goes up and down every year. It goes up as plants aren't using it because of northern hemisphere winter. It goes down northern hemisphere summer. Then we're into fall. They drop their leaves. CO2 starts to go back up. So this is the annual pattern is higher CO2 in the spring, lowest CO2 in the fall. But the year-to-year trend is just up and up and up and up and up and up and up. There have never been humans alive at a time when we've had this much carbon dioxide in the atmosphere. How do we know the climate is changing? Every possible way. If there is something you could say, well, if the climate's getting warmer, what would you expect to see? We're seeing all of that. If you said, hey, if the climate was actually getting colder, what would we expect to see? We are not seeing any of that. So what do you have? Higher air temperatures, higher surface temperatures, higher ocean temperatures. So the temperatures are up over the land, temperatures are up in the atmosphere, temperatures are up in the ocean. There's more heat stored in the ocean. There's less ice in the ocean. There's less ice on the land. The melting ice on the land is causing rising sea levels. And there's increased water vapor. So every measurable objective criteria that we could use to look at is the climate changing says, yes, the climate is warming. The climate is warming. Here is a grid version of the animation I showed you earlier. Temperature change per century from 1900 up to 2012. You can see much more warming at higher latitudes than at lower latitudes. And that big blob of cold water coming off of Greenland. Here we've got the temperature record going back to 1880. 2016 was the warmest year ever recorded. The 2000 were the warmest decade ever recorded. The 2000s broke the record. Well, the 2010s are going to obliterate the record set by the 2000s. The 2000s obliterated the record set by the 1990s. The 1990s obliterated the record set by the 80s. So every decade from 1980 on has been the hottest decade ever measured on Earth. And there's no signs that this is slowing down. Sea ice, record low levels of sea ice. I put a video. NASA has a really cool animation of year-to-year sea ice. So the volume is decreasing, the area is decreasing, the ice is covering a smaller area, which then puts in motion a positive feedback loop because the ice is thinner and there's less of it, so the ocean gets warmer. So the ice forms later in the year, so it's thinner. So it melts faster in the spring, so the ocean soaks up more heat, so it freezes over later in the fall, so the ice is thinner, which is a really big deal for marine mammals like polar bears that require multi-year ice. This sea ice is made by frozen seawater, and every year that ice, if it sticks around, has the chance to get thicker. So the older the ice is, the thicker the ice is, and the ice that we have the least of is the old ice. Almost all the ice now is very young, very thin ice that won't support the weight of polar bears or walruses or seals. So we're seeing massive, 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 unprecedented change in the Arctic. Greenland, back in 2012, 97% of the Greenland ice surface was melting. This is another possible feedback loop, the ice elevation feedback loop. So you know it's cool to be high. As you go up through the atmosphere, as you get away from sea level, the air is cooler. So the ice sheet in Greenland is like 10,000 feet thick. It's really thick. It's really high. Because it's so high, it's very cold. It's melting. As it melts, the elevation of the surface comes down as the ice gets thinner, so it's warmer. So it melts more, so the elevation of the surface gets lower. So it's warmer, so it melts more. There's a chance that we might have turned the tipping point on the Greenland ice sheet, that it is just going to continue to melt forever until it is all gone, and in 100,000 years we go back into another glacial cycle. Greenland, you can see, losing about twice as much ice as Antarctica. And in both cases, there's just a steady trend. I haven't seen too many where they, instead of looking at the mass in gigatons every year, of reversing it, saying, this is how much we have, and here's the zero, so when are we going to run out? Oh, right, ice shells. Yeah, so all of this stuff is ice that is grounded to the surface. This is ice that has flowed off the land, and it's floating in the ocean as a continuous surface. So it's like a huge sheet of floating ice, another huge sheet. All the colored spaces are huge sheets of floating ice. Many of them are breaking up. And when they break up, because they're in the ocean, they don't increase sea level. But when they break up, the ice that's on the land flows faster into the ocean. So some big effects there. Here's a side view showing the floating ice sheet. So this would be the colored section. In fact, which one are you looking at? It doesn't matter. So we could be looking at this ice sheet. Here is the grounded section, and here's the floating section. So here's the floating section, here's the grounded section. And then warm water gets in and melts back at the grounding line. And as the ice is exposed to the ocean, it breaks up easier. The thinner the ice is, the more fragile it is, the easier it breaks up. So that's another positive feedback loop. Permafrost. This is ground that is permanently frozen, and it has organic material. When it thaws out, the organic material gets broken down, and they make it into methane, the microorganisms. You can burn methane, but methane is roughly 26 times more powerful than carbon dioxide. I've got a video. This is Dr. Katie up in Anchorage in the University of Alaska. She does research into methane. These are trees that are falling over because the soil has thawed out, that there was ice in the ground under the soil that acted as a support. Now it's melted, so the trees fall over, and then they rot, which generates more methane, which is a greenhouse gas. So I would check out Dr. Katie's video. It's short, it's really interesting. Talks about how much methane is coming out of the permafrost. And here is a more recent study done showing kilograms of organic carbon in the soil in the top 30 centimeters per square meter. So the darker the color, the more carbon there is to be released as it thaws. And then looking at glaciers and permafrost and how thick the permafrost is. The bottom line to this diagram is there's a lot of carbon in Canada and permafrost, and it's going to melt and get released to the atmosphere. More permafrost. As it thaws out, we're looking at potentially 1.7 gigatons of carbon being released by thawing permafrost. Sea level rise. We're looking at about 6 feet. As the ice on the land melts and runs into the ocean, sea level rises. As the water in the ocean gets warmer, it expands and sea level rises. And I think best estimate is by 2100, we're looking at about 6 feet of sea level rise. This is a Pacific Island nation. This is the road, and this is the ocean. This is high tide. This is not like an exceptional storm. This happens every day. And these people get their water from rainwater, and some of these islands have lakes. And as the sea level is coming up, their fields are being contaminated with salt water. So they're literally going to have to move entire nations. There are entire island nations that are trying to make agreements with New Zealand or Australia to accept hundreds of thousands of climate refugees. Storms are bigger. I believe this is Hurricane Patricia, sustained winds over 200 miles an hour over Mexico. It was the largest, most powerful hurricane in the Pacific ever recorded. It's just a symptom of a warming planet. Tornadoes, also North Atlantic hurricane strength, and sea surface temperature going up and up and up. Since from 1970 to the present, from 1970 to the present, the energy released by storms has doubled. Not the number of storms, but the energy released by hurricanes has doubled. At the same time, the sea surface temperature warmed by about a degree. So a degree of warming in the ocean results in a doubling in hurricane power. Flooding. Well, the places that aren't having flooding are having droughts, lots of drought severity because of warmer temperatures, increased evaporation. So even if they get the same amount of rain, if it's warmer, they could end up in a water deficit because there's insufficient precip to meet the needs of potet. Right, the causes, mainly carbon dioxide. Here we've got, again, the Keeling Curve, carbon dioxide 1958 to the present, up and up and up. Concrete, this is a factory that's making concrete, or cement rather. Cement requires enormous amounts of fossil fuel to make. Before I started studying climate change, had no idea that the cement industry is a driver of climate change. Methane, mainly from natural gas fracking and natural gas and agriculture. Methane is 26 times more powerful than carbon dioxide at absorbing heat. Nitrous oxide, mainly from synthetic fertilizers, another source of greenhouse gases in the atmosphere. CFCs, chlorofluorocarbons used as refrigerants in refrigerators and heating systems for homes, another source. Tons of oil per capita, we're up there. US, Canada, Australia, and Saudi Arabia, using lots and lots and lots of oil. I put radiative forcing really big. Radiative forcing, or RF factors, make the climate warmer or colder. So positive radiative forcing makes it warmer. Negative radiative forcing makes it cooler. So scientists looked at the relative amounts of warming from blue is carbon dioxide. So you can see the majority of warming from greenhouse gases is carbon dioxide. Number 2 is methane. And then they looked at everything. Really, they've been looking at everything for decades. Greenhouse gases, warming, and so they've converted everything to the equivalent warming in watts per square meter. And you might remember watts per square meter when we were talking about insolation, energy coming in from the sun oh, there you go. So at the Sacramento in the summer, I think we get about 400 watts per square meter per day. So these are relatively tiny changes, but averaged out or multiplied out over the whole planet, greenhouse gases have warmed the planet by 2.8 watts per square meter. More water vapor, 0.07 watts. Tropospheric ozone, 0.4 watts. Clouds, contrails, 0.5. Black carbon on top of ice, warming. And then there's some negative factors like aerosols. Air pollution, almost half a watt of cooling because of aerosols. But if you put everything together, the overall trend is humans are warming the planet. There you go. So the bars on the right side indicate warming. The bars on the left side, these would be negative forcing. So air pollution and aerosols. Aerosols in the atmosphere, that's air pollution. And then the positive factors are greenhouse gases, mainly carbon dioxide, methane, other gases, contrails, black carbon. All of those add up to about 2.4 watts per square meter. So the total radiative forcing is about 2.4 watts per square meter. Scientists look at everything. So the black is what actually happened, and the red is what the computer models said should have happened. And the computer models are looking at natural and man-made drivers or human-made drivers to climate. So changes, this is energy from the sun and going up and down on amount of 0.1 Celsius degrees, so 1/10 of a degree of warming and cooling from changes in the sun. Volcanoes cooling by like 0.15 degrees. El Nino plays a small role, but overall, the overall trend, warming and warming and warming. This is a picture. This is funny. This is a picture that is of a computer model, and the computer model is a computer program that's supposed to simulate the way Earth works. So the picture is a simulation of a computer program that's a simulation of Earth. So it's a model of a model. You can see they divide the whole world up into this grid, and then they see what's happening in each grid square, and then they make changes and see how everything is affected. And by doing that, they can perform experiments with Earth. Like if you increase low clouds by this much in these places, how does that change the climate of Earth? Or if there was more CO2 or less CO2 or more ice or less ice, they can make all those changes in the computer model and then see what happens. They can also use reality as a check on the programs. So they can go to like 1900. We know what the conditions were on Earth in 1900 for things like temperature, air pressure, relative humidity, wind speed and direction, cloud type, water temperature, ocean currents. So they can set it for January 1st, 1900, and then just let the computer model run on its own without making changes to it to see how closely the model approximates reality. And then by doing that, they can make tweaks to the program. Since we've got reality that you can run the program against to check to see how it worked. In fact, the BBC did this hundreds of thousands of times. They allowed people to download these computer programs that ran on their home computers and then uploaded the results. And they took the best results and they tweaked them, and then they sent those programs back out to everybody. Then they took the best running programs, made tweaks, and sent those back out. So over hundreds of thousands of iterations, the models are getting much more sophisticated. As computers get more powerful, the boxes get smaller and smaller. So instead of just a few boxes covering the whole United States, now one box is covering Sacramento, and one box is covering Vacaville, and one box is covering San Francisco, whereas before one box would have covered like all of California. So the results are getting more precise, the results are getting more accurate, and the results are getting more alarming. There's a picture of a computer, whatever, it looks like a box. So looking at the observed versus the climate models that only looked at natural factors, there's very poor agreement. If you look at the black line of what really happened and the red line is the climate models, including natural and human changes to the climate, there's very good agreement. Right. So these are RCPs, Relative Concentration Pathway Models, RCP, Relative Concentration Pathway. And there's the numbers, I was going to say there's like four. There's 2.6, 4.5, 6.0, 8.5. The numbers represent watts per square meter of warming. So the current amount of warming is 2.4 watts. So this would be like today. So we stop emitting emissions today. Everything shuts down today. Amount of CO2 stays the same, and so does temperature. 4.5, 6, and 8.5. The reason that there's different models, the reason that there's these different projections is not that scientists don't understand the climate. Scientists understand the climate very well. The reason that there's four different models that they keep running are because scientists don't know how humans are going to respond. Like the difference between these models is how aggressively we stop using fossil fuels. The worst case scenario, the RCP 8.5, isn't bad enough. It underestimated how much CO2 we'd actually be putting out. And that one is calling for 8 Fahrenheit, 4 Celsius by 2100. I think it's the course that we're on. This is the business as usual. Let's just burn it all now. So the reason that there's different models is because scientists don't know what choices society is going to make. The numbers in the different models represent watts per square meter of warming. Here we've got another version of the same thing, slightly cleaner. You can see they're doing hundreds of different model runs using different initial conditions, different fudge factors in the models. So here we've got 8 degrees, 8 Fahrenheit by 2100. But it just keeps going up. And this might be what's going to happen regardless if we were wrong about some of the feedback loops. So here's what the difference makes. By 2100, with a 2.6, the strong mitigation, we're looking at a degree or a degree and a half. Under the business as usual, which is the one that we're on right now, we're looking at 4 or 5 degrees. 4 or 5 in the mid-latitudes, and in the Arctic, almost 20 Fahrenheit degrees of warming in the Arctic. And the Arctic is now experiencing large ice-free events. So we could see the end to Arctic sea ice in the summer, for example, sooner than we thought. This is what it looks like if Earth is 4 degrees cooler. If Earth is 4 degrees cooler, you can walk all the way from Indonesia or from Malaysia down into Indonesia Again, no English Channel. The coast was 60 miles offshore. You could walk to the Farallones. That's what 4 degrees cooler looks like than present, and we're going 4 degrees warmer. 4 degrees warmer, all of the red stuff is probably going to be underwater because of sea level rise. In fact, all of the yellow, with that 6 feet by 2100, Miami, I've put a couple videos about Miami because Miami hasn't figured out that it's doomed yet. They have many multi-million, I don't know, million, billion dollar buildings, condos, for example, hotels, resorts that are at sea level. And as the ocean rises, they're going to be worthless and nobody will want them and nobody's going to buy them. And so the people that own them won't be able to sell. Nobody would buy it because no bank would give you a loan for a house that's literally underwater, to say nothing of an investment property that's literally underwater. And then the cities that get the revenue from property taxes aren't going to have money for city services. It's a multi-trillion-dollar disaster that is coming, and we're not doing anything about it currently. We're looking at, I'm going to say, about 6 feet of sea level rise by 2100. This is New York City after Hurricane Sandy. This is just the ocean. New York is spending about $2 billion on hurricane-proofing the city, to increase the height of walls, to flood-proof the subways. It would have been way cheaper if we had just stopped using fossil fuels, but we didn't. So how do we know? Well, because the scientific studies, they've looked at everything. They're 99% certain. They are now as certain about climate change as we are that cigarette smoking causes cancer. I heard that and I thought, oh, that's good news. And I thought, no, it's not, because like 19% of the American public still smokes. So 19% of the American public said, well, yeah, those cigarettes can kill me, but I don't care. Or maybe they said, I don't believe it. In any event, about 19% of the American public smokes, or adults anyway. So scientists are way more certain of climate change than many other things. Scientific consensus. So this is an old diagram, but I kept it here. This is one of those studies that looked at almost 14,000 peer-reviewed climate change articles, and they found 24 that rejected global warming. I actually read one of them, and it was a Russian publication, which is interesting because the Russian economy is largely built on fossil fuels, natural gas, and oil. So this Russian article started by saying, well, if this global warming thing is true, then that's going to be really bad for the Russian economy. Here's why it can't be true then. And I thought, well, that's a load of bunk. I also just read another study that said that those 24 studies, they could not reproduce the results. Independent scientists attempted to reproduce the results that these studies got, and they discovered flaws in the study. And if you correct for those flaws, you cannot reproduce the results. So really what this is 14,000 articles about climate change and none that actually reject global warming. I would point out all kinds of things, like the group of people that has the best data that would show that it's not being caused by humans would be the fossil fuel industry, because they've dug wells all over the world, so they have geologic evidence that would, if it was something other than fossil fuels, they would be able to say, oh, it's not fossil fuels, it's this other reason, but they hadn't. Anybody that could support that would be instantly financed by the fossil fuel companies. They would win a Nobel Prize for disproving anthropogenic climate change, but none of that's happening. So every year it's more and more certain that we're changing the climate and it's bad. Cold weather causes more people to disbelieve global warming. Climate change, that the planet's completely clear that it's warmer. What could we do about it? Well, renewables. Renewables are the cheapest way of making electricity. There's absolutely no economic rationale for building a plant to make electricity using anything other than renewable resources. Changing our agriculture from conventional factory farming to organic sustainable agriculture would take up that extra carbon dioxide that humans are emitting. We could literally stop climate change if we supported organic family farming. Really, that's just mind-boggling. But we're not going to, because the fossil fuel companies are making trillions. Geoengineering is something that really frightens me. I'll be completely honest about that. That's the idea that we should undertake massive, massive, massive projects to change Earth's climate. Like, well, heck, we know that dust in the atmosphere cools the planet, so let's put real chemtrails. Let's put gunk into airplane fuel so that when they fly around, they leave more or less permanent chemtrails that'll increase the albedo of the atmosphere. And hopefully it'll turn out good. Let's fertilize the oceans so that algae soak up carbon dioxide from the atmosphere and die and sink to the bottom, taking the CO2 with them. Let's put a giant umbrella in space and block the sun. All of these ideas, I think, as the climate crisis continues to get worse and worse and worse, will be seen as more popular. Like, I don't want to stop driving. Let's just put a reflector in space. What can you do? Turns out just about nothing. I mean, all of these things are good. I have solar panels on my roof because it's just the right thing to do. I drive an electric car because it's cheaper. So you might have heard of ecological footprint or carbon footprint quizzes. I just found out those were started by the fossil fuel industry to make you think it's your fault. I was so pissed when I found that out. And I thought, oh, of course. If they're trying to tell us it's us, it's not us. This is action that has to be taken at the governmental, at the international scale. This requires international cooperation between governments. But if they can convince us that it's our fault, then that won't happen. But it's going to require international cooperation to slow and possibly reverse climate change. Yeah, Rolling Stone had a cool article. They do good articles about Miami and sea level rise. And that's pretty much it for the chapter. The too long didn't read. Climate changed in the past because of Milankovitch cycles. We know what happened in the past because of proxy data. And the changes right now are mainly carbon dioxide from burning fossil fuels. That's it. I hope you enjoyed the climate change chapter, and good luck.